Somewhere deep in our tangled ancestry, there must have been the very first philosophers, maybe even millions of years ago, with their identities forever beyond our grasp. Some might have cared about more than just the next meal, and began to wonder about the very nature of reality around them, and question their existence. Those who first wondered, staring at a starry sky, where did it all come from? This question has dogged us for all of human history, through the rise and fall of civilizations. For some, it fueled creation myths and gave birth to religions. Hoping to make sense of it all, wise sages have always debated the meaning of existence and the reality of consciousness. But with the coming of the scientific revolution, our understanding of existence began to change. It was the scientific great Isaac Newton who declared that the laws of physics must be truly universal, and that the same law of gravity that pulls the apple off the tree must also hold the moon in its orbit. He stated that the laws of nature right here on Earth reach out across the entirety of the heavens. It is a clockwork universe, he said, with no need for gods or monsters to drive the celestial. This picture of a cold and uncaring universe, with no true goal or purpose, was unsettling for many. But as the revolution gathered steam, scientists continued to dissect the workings of the cosmos. Telescopes revealed the immensity of our galaxy, the Milky Way, home to hundreds of billions of stars, and discovered the vastness of the observable universe, home to maybe 1 trillion other galaxies. However, the nagging question of where it all came from and where it's all going remained. Perhaps the universe had just been around forever and would be around forevermore. Perhaps nothing ever really changed, and the universe just is as it ever was. But it became clear that such an eternal cosmos was forbidden by the rules of science themselves. The 19th century had seen the birth of thermodynamics, the rules of efficiency and heat flow. And this showed that decay and inefficiency are fundamental properties of the working universe. Everything is winding down and wearing out. And this includes the cosmos itself. So if it is eternal, why isn't the universe now in a state of complete chaos and disorder? By the 20th century, things began to change, and this change came rapidly. As theoretical understanding bloomed, powerful new telescopes began to scour the skies. The greatest minds were focused on understanding the workings of the universe. From the subatomic to the cosmic, secret after secret was ultimately revealed. And it finally seemed that the ultimate origins of the universe were just within our grasp. On the 20th of June 1966, Georges Lemaitre died. He was aged 71. Shortly before his death, he had been brought news of a strange new scientific discovery. He was told that the entire sky glowed with unearthly radiation, microwaves from the depths of space. This made the old man happy, showing that he was right about the origins of our universe. He was right in declaring that our universe had a beginning. Lemaitre had faced argument and condemnation for this, accused of trying to stuff religion into science. His role as a Catholic cleric, with his pronounced dog collar, really didn't help in this regard. He was also a gifted mathematician, and 4 decades earlier, he became the first modern cosmologist. In the 1920s, he pieced together the foundations of our understanding of the universe. Lemaitre was an early adopter of the general theory of relativity, Einstein's scientific magnum opus. Einstein had replaced Newton's gravitational forces with the bending of space and time themselves. This insight into reality propelled Einstein to the position of scientific superstar. And Einstein was certain he could write down the mathematics of the entire cosmos. But Einstein was convinced that our universe was eternal and unchanging, using this as his starting point. Lemaitre watched Einstein's convoluted mathematical gymnastics to try to make this work. And then Einstein's arguments with Alexander Friedmann over whether the universe could be static. Friedmann won the argument, but all of this seemed like nothing more than theoretical cosmic musings. Lemaitre also kept his eye on the observations of the universe. In particular, those of Edwin Hubble. Hubble was using the world's largest telescope to map the distances and speeds of distant galaxies. Without anything to guide him, he expected galaxies to be buzzing around like a swarm of angry bees. Instead, he found that galaxies were all moving away, and the further they were, the faster they moved. In front of him, Lemaitre suddenly had the 2 vital pieces to understand the universe. He had Hubble's confounding observations that seemed to make no sense. But he also had the mathematics of a relativistic universe and understood exactly what it predicted. And when he compared the 2, theory and observation, he found that they matched. Lemaitre realized that this must mean we live in an expanding and evolving universe. Lemaitre's conclusion came as a shock to our view of the universe. Hubble himself never accepted this cosmic idea and focused on peering through his telescope. But Lemaitre realized that if the cosmic expansion means that the universe is larger tomorrow, then yesterday the universe must have been smaller. With the mathematics of the cosmos in hand, Lemaitre was able to theoretically wind back the universe and determine the size of the universe as he looked further and further into the past. Looking back over billions of years, the universe was smaller and smaller, until, ultimately, he hit the point where everything was in the same place and a precise time. This, Lemaitre declared, was the cosmic egg, the origin of the universe. The notion that our universe possessed a moment of creation further shook the scientific world. To some, this creation reeked of religion, echoing the Book of Genesis and God's hand in cosmic birth. And it was here that Lemaitre's role as a Catholic cleric was turned against him. In 1949, cosmologist Fred Hoyle disparagingly called Lemaitre's view the Big Bang Theory, and this was a name that stuck. Others, however, embraced this picture of ultimate cosmic birth, of space, time, and matter, with the realization that the initial moments must have been hot and dense, like a cosmic nuclear reactor. In the first minutes, from the simplest fundamental pieces, the cosmos cooked the first chemical elements, sowing the seeds for all of the stars and galaxies, planets and people, seen across the heavens today. The initial cosmic fires were blazing hot, a trillion-degree soup of particles and high-energy light. But as the universe expanded, it cooled and settled. And after millions of years, the first stars formed. The light from creation remained, filling the void between the stars, but always cooling to lower energies. This light should still be with us today, cooled from ultra-high energy gamma rays into cooler microwaves. Astronomers had realized that this relic radiation should still be out there, still bathing the Earth today. And through the 1950s and into the 60s, experiments were devised to hunt for this faint glow. It was finally spotted in 1964 with a telescope in Homedale, New Jersey, and it was found by a pair of scientists who weren't even looking for it. Arno Penzias and Robert Wilson were planning to repurpose a communication receiver into a telescope. Known as a horn due to its distinctive shape, this telescope peered at radio waves coming from the sky. And Penzias and Wilson worked hard to reduce the inevitable hiss created in their warm electronics. But no matter how hard they tried, one stubborn hiss could not be controlled and quietened. They even removed pigeons nesting within the horn, and the white dielectric material they left behind. But they eventually concluded they were picking up a signal from deep space. A signal that seemed to come from all across the sky. A uniform glow of radio waves. And a quick phone call to nearby Princeton University revealed the significance of their uniform radio hiss. This hiss sent Penzias and Wilson to Stockholm to collect a Nobel Prize in 1978. It was news of this background radiation that was brought to Lemaitre shortly before his death. These cosmic microwaves were the afterglow of the initial fiery event of creation. And it was from this initial fireball that all the matter of the universe ultimately emerged. But it also meant there was a first day, a day of creation, a day without a yesterday. And cosmologists were now faced with a daunting question. Just where did the universe come from? Modern cosmology is undoubtedly a modern scientific success story. Successfully explaining the life of the universe from fractions of a second through millions of years. So you might be surprised that cosmologists have so far failed to divine the birth of the universe. Their complex equations and deep observations have not revealed our cosmic origin. Their failure is due to a deeper failure in our understanding of the cosmos. A scientific embarrassment that has dogged modern physics for more than a century. At the heart of this embarrassment is that 20th century physics is built on two distinct pillars. And these pillars, the basis of all of modern physics, simply refuse to work together. We've already met one of the pillars, Einstein's general theory of relativity. It is with its description of gravity as curving and bending space-time that we use to describe the universe. At the other end of the scale, the subatomic world obeys the rules of the other pillar, quantum mechanics. And instead of curving space, quantum mechanics sees the world as probability and wave functions. Whilst both theories are wildly successful, they are mathematically incompatible. Written in mathematical languages that are more different than Mandarin is from French. Most of the time, physicists don't have to worry about the differences in these theories, as it's usually clear that what they're trying to understand is subatomic or cosmic. Except, that is, when cosmologists are trying to understand the very early universe. Here, space-time was rapidly expanding, whilst quantum forces raged between matter and radiation. In this boiling sea of the fundamental forces, their distinction and individuality was lost in the tumult. And it is thought that a single force, the cosmic superforce, ruled the embryonic cosmos. This superforce sits above the realm of quantum and relativity. Neither one or the other, but a more pure state that encompasses them both. As the universe expanded and cooled, the superforce splintered into the familiar forces: gravity, electromagnetic, and nuclear forces. But in the earliest stages of the cosmos, this superforce defined the birth of the universe. Physicists have hunted for the language of this superforce, the theory of everything, for more than a century. Many ideas, from extra dimensions and supersymmetries, superstrings and loop quantum gravity, have been proposed, worked on, and discarded, cast into the scientific waste bin. And after many missteps and dead ends, the theory of everything, if it even exists, still eludes us. Without this theory of everything, physicists are at a loss on how to approach the moments of creation. There is a door that remains locked due to our inability to crack this mathematical puzzle. We cannot unravel what was happening before a trillionth of a trillionth of a trillionth of a second. And the very birth of the universe remains hidden from us. It seems that we've already reached the end of our story, stuck in front of a mathematical door as our smartest minds scrabble for the mathematical key. But what will we find if we finally crack the puzzle and push on the door of ignorance. What could we find about our ultimate origins, about what came before the universe? Let's take a look at what opening the door might finally reveal. Maybe Terry Pratchett, the author of the Discworld series of books, was right. His strange cosmos is home to a flat planet, carried by elephants, riding on the back of an immense turtle. This world is filled with weird and wonderful characters. Some who wondered about the creation of the universe. And their view, in the beginning there was nothing, which exploded. Some physicists have proposed that when we pry the door open, we will ultimately find nothing. As we push backwards in time towards the ultimate origin, we will find a hotter and denser universe. Eventually, we'll find a point where temperature and density soar to infinity. All of space and time crammed into this infinity. And before this, nothing. This is not a nothing that you would probably be happy with. It is not a nothing like the emptiness of the vacuum off in the deepest points of outer space. This is a true nothing, not just an absence of substance and radiation. It's an absolute nothing. A nothing of no time and no space. Such a nothing is difficult for us to imagine. As clocks and rulers set the stage for the universe, what does it mean to have no space and no time? And what caused the universe to come into being? How can we even talk about such a nothing without some kind of reference we can point to? And how can this complete absence of anything even explode into the universe around us? As you might imagine, this is a realm where physicists and philosophers often clash. Arguments about the meaning of nothing might seem, well, meaningless. But the meaning of nothing often depends on who is talking about it. And this has left some wiggle room for physicists to propose an ultimate origin of the cosmos. It was in the early 1970s that physicist Edward Tyron proposed a solution to the conundrum. The answer, he said, was in quantum mechanics. The probabilistic laws of the subatomic universe. The nothing that preceded the universe, he said, was a distinctly quantum nothingness, where even the meaning of space and time was fuzzy and undefined due to the action of the quantum. The nothing that preceded the universe, he said, was a distinctly quantum nothingness, where even the meaning of space and time was fuzzy and undefined due to the action of the quantum. The quantum nothingness is a broiling sea of fluctuations, probabilistically popping in and out of existence. As well as matter and radiation, space and time emerge and vanish within the mix. But quantum mechanics stipulates quite strict rules of these fluctuations. And the fluctuations in space and time would be, to our sensibility, microscopic. You only need to look to see that our universe is awash with energy. Huge quantities of it, in many forms. So if the origin of our universe is somehow a quantum fluctuation, surely it should exist for only an instant. This might be the case, but Geraint stated that we had missed something crucial about the makeup of the cosmos. The universe, he said, actually contains no energy at all. You might think that this is crazy, but Geraint is using energy accounting to reach his conclusions. Yes, there is all that energy out there, energy in motion, in heat, in light, in matter. But another energy out there, spread across the entire cosmos, known as potential energy. And it is this potential energy that holds the key to the universe. Potential energy is the energy stored in the way that stuff is arranged. Two rocks, separated in space, are drawn together due to the gravitational attraction between them. And as they fall together, the faster they go, gaining energy of motion as they fall. This kinetic energy is tapped from the potential they had from being separated in space. Potential energy, however, is a curious thing when compared to other energies. The energy of heat and motion are positive quantities, a positive number of joules. The potential energy of gravity across the cosmos is, however, a negative number of joules. This is to reflect the fact that you need to input energy to drive masses apart. So across the cosmos, therefore, there are both positive and negative energies. And if we sum these two, Geraint states, they exactly balance, and the total energy of the cosmos is zero. If our universe was born in a quantum fluctuation, then it is a fluctuation of zero energy. And so, if it is a fluctuation, according to quantum rules, it is a fluctuation that can exist forever. Just how realistic is this accounting trick with the energy of the universe? Can our universe really be a long-lived quantum something popping into existence from nothing? Philosophers argue that all the physicists have really done is push the origin question elsewhere, into the origin of the quantum fuzz from which the cosmos emerged. Physicists rarely let the worries of philosophers bore them, ignoring them and moving on, and many have sought the origin of the universe as a crystallization out of the quantum. The late Stephen Hawking thought our universe burst from a place where time and space lost meaning. From a place of nothing but quantum probabilities and uncertainty. If this quantum origin of our universe is correct, other questions remain. The most intriguing being whether the fluctuation that formed our cosmos is a one-time event, or did it happen over and over again? And our universe is not alone in the quantum fuzz. Maybe it's awash with universes, a multiverse of universes even. But we're getting ahead of ourselves, and we'll return to the story of multiverses very soon. But now, let's turn to a case of cosmic déjà vu, and wonder if we have been here before. Paraphrasing the poet Robert Frost, some say the world will end in fire, whilst others reckon ice. It appears our universe was truly born in fire, but what does its future hold? Fire or ice? All of our observations tell us that our cosmos will expand for eternity, forever growing and cooling. And it appears that our universe in particular will certainly end in ice. This wasn't always the viewpoint of cosmologists as they struggled to understand cosmic evolution. Early observations could not precisely determine the future expansion of the universe. So there was a possibility that our current expansion could grind to a halt and reverse into collapse. And through this collapse, the end of the cosmos would definitely be one of intense fire. A collapsing universe would be the reverse of our currently expanding cosmos. And instead of cooling, the shrinking universe would heat up, ever so gently at first. But as the collapse rushes towards its ultimate end of infinite temperature and density, the temperature would soar through millions, then billions, then trillions of degrees. As we have seen, in this state, gravity and the other quantum forces will battle for dominance. And maybe in this boiling sea of matter and energy, the quantum will prevent the ultimate collapse. Densities and temperatures might soar to unimaginably high values, but they will never reach the infinities that mark the universe's final demise. If space and time don't completely collapse, then what could possibly happen? Maybe it rebounds in the halting of the collapse, with the collapse becoming a new phase of expansion. This would be another hot and fiery Big Bang, a new moment of creation, a moment of cosmic rebirth. And from that creation would emerge atoms and then stars and maybe life, and maybe us all over again. The expansion of this new incarnation of our universe would be destined to halt and then start to collapse. Back into death by fire, before again rebounding and being born again in fire. And if this cosmic cycling is destined to be the future of this universe, then so it was in its past. The present life of the universe would be just one of an eternal cycle of cosmic birth, cosmic life, and death. Again, many will be angered by cosmologists simply moving the goalposts. Just what is the origin of this ever-cycling universe? Just where did it come from? But cosmologists can point at the infinite past and infinite future and smile. You can hide a lot of your problems under the immensity of infinities. At this moment, you might be experiencing your own episode of déjà vu. We've met the idea of eternal universes before, way back at the very beginning of our story. Weren't we told that over eternity, the universe would be steadily winding down as entropy grows? If it has existed into the infinite past, how can it be home to order structure, and life in this incarnation. Some have suggested radical ideas to address this, that time itself reverses during cosmic collapse. In such a collapsing universe, disorder would rearrange into order, with entropy decreasing. So when it's reborn, it is reborn young and fresh, without the scars of disorder of its predecessor. For most, however, this notion is too radical to save the ever-cycling cosmos. But why should we worry about this notion, as we know that it doesn't represent our universe? We know that our universe is not going to collapse, instead being destined to expand forever. Surely we are looking at an end in ice, not fire. A future universe of nothing but cold and emptiness. But that is not what every cosmetologist thinks. Paul Steinhardt named his model for his cosmology the ekpyrotic universe. Ekpyrotic in Greek means conflagration, a raging wildfire. And this is how he sees the life of the cosmos. In 2001, Steinhardt and collaborators presented their cosmology to the world. An infinitely repeating cosmos that doesn't appear to suffer from the decay seen in others. The ekpyrotic universe is built on the ideas of M theory, or membrane theory. With this, the fundamental universe is composed of sheets of space and time floating in higher dimensions. Two such infinite sheets are floating out there. One of them is our universe, the other is another. And these sheets are thrust apart in a creation event, a Big Bang. Within these sheets, the universes expand and cool, and stars and galaxies form and live out their lives. Eventually, these universes age, and expansion thins them out, driving them to almost zero density. In the higher dimensions, the two universal sheets are steadily drawn back together, slamming into each other and reigniting a new event of creation, a new Big Bang, and the cycle continues. What about the problem with entropy and decay? No problem, says the ekpyrotic supporters. All that disorder is simply washed out in the immensely expanded membrane. Out of sight and out of mind, again, the problem has been swept into the reaches of infinity. And each newborn cosmos is pristine and pure, untainted by the experience of its ancestors. However, the majority of cosmologists are not convinced by this neat-as-a-bow picture. Of course, the ultimate origin of the cycling universe remains completely unexplained. But why should the picture be limited to a single pair of universes colliding in higher dimensions? What if our universe is part of something bigger? A universe of universes. For many, our ultimate origin resides somewhere in the multiverse. Robert Dicke was one of the most insightful minds of the 20th century. It was he who received the phone call from Penzias and Wilson and realized what they had found. He had been driving the team at Princeton to measure the cosmic microwave background radiation. If it wasn't for their accidental discovery, it could have been Dicke in Sweden collecting the Nobel Prize. Dicke thought deeply about the universe, in particular, a strange insight from physicist Paul Dirac. Paul Dirac, a founder of quantum mechanics, collected his own Nobel Prize in 1933. But he also noticed a strange coincidence between some of the fundamental properties of the universe, and with just how old the universe appeared to be. There are certain fixed numbers, the fundamental constants, that are essential for physics to work. These include the speed of light, the strength of gravity and the other forces, and many more. Dirac combined some of these fixed numbers and found an answer that matched our cosmic age. And this was very strange and very confusing. The constants of physics are, well, constant, and so their combinations don't change. But the age of the universe is constantly changing every second. How can these two numbers with radically different origins be of the same value? Either this was some strange coincidence, or maybe the physical constants are changing with time. Dirac's suggestion that the fundamentals of physics are changing was not well received, and many thought that his finding was just some strange numerological coincidence. But Dicke realized that the coincidence of these numbers was telling us something deep, something that would actually shake the foundation of our universe to the core. One of the key concepts in our understanding of the universe is the Copernican principle. The idea is that we are on an unremarkable planet orbiting an unremarkable star. This unremarkable star, our Sun, is in an unremarkable part of the galaxy, in a wholly unremarkable and completely average part of the universe. This picture began to emerge when Galileo displaced the Earth from the center of the universe. And astronomical observations that revealed the Sun was just a star, just one of the billions that litter the Milky Way, and the trillions across the heavens. The Copernican principle simply says that we are just in an average bit of the cosmos. Building on this idea, Einstein and others were able to mathematically deconstruct the universe. And the Copernican principle, our averageness, still stands at the heart of our cosmological theories today. But Dicke realized that Dirac's insights meant that the Copernican principle must be flawed, because we simply can't exist at a typical and average time in the life of the universe. Dicke realized that we could not have existed in the earliest epochs of the universe, as there was not enough time to build heavier elements like carbon in the hearts of stars. If you calculated the time needed by stars to fuse and disperse elements in stellar generations, it depended precisely on the combination of fundamental constants identified by Dirac. The apparent numerical coincidence is not a coincidence at all, as we simply could not have existed at another time when the values did not match. Dickey argued that there is a selection effect, an additional constraint on our presence, that has to be applied across the Copernican principle to explain our view of the universe. And so, one of the most controversial ideas in all of physics, the anthropic principle, was born. The anthropic principle states that our location in the universe, in both space and time, must be privileged. If we consider the factors needed for our existence, such as carbon or being near a stable star, we simply cannot expect to find ourselves at any random location in the life of the universe. Our viewpoint of the universe is not simply unremarkable. It has to be, in some sense, special. Some have pushed the anthropic principle even deeper into the physical laws of the cosmos. As mentioned, these rely on the fundamental constants to define how physics operates, such as setting the strengths of fundamental forces and masses of elementary particles. But our physical theories don't tell why these numbers have the values they have. We can imagine universes where these values are different, with different laws of physics. We can picture a universe where the electron was 100 times more massive than in ours. Or a universe without gravity, or super-strong electromagnetism, or a mix of many other changes. But a stark picture emerges across these hypothetical universes. Nearly all are dead and sterile. There are many ways to kill the prospects of life and habitability in a hypothetical universe. It could simply expand too fast for matter to coalesce into stars and galaxies. Or maybe where gravity is too weak to ignite stellar cores and make heavy elements. Or even where a universe lives for only a tiny fraction of a second, before collapsing back into nothing. The laws of physics of our universe seem just right to allow us to be here. A Goldilocks universe. This puzzle, known as cosmic fine-tuning, has led to further arguments around the anthropic principle. To some, this statement carries no weight, simply being little more than a tautology. Where else should we expect to find ourselves but in a universe that permits us to be here? For others, the question of just why we have the laws of physics that we do is confronting. Just saying that it has to be the way it is because that's what it is very unsatisfying. What if Dickey's anthropic principle has a much broader reach over all the conditions of the cosmos? What if we are here because there is a selection over universes, and that we live in a privileged cosmos? But just what does it mean to make a selection over universes? And where is this selection made? And does this mean that all of these hypothetical universes are not actually hypothetical at all? And if they are real, just how many of these hypothetical universes are out there? The anthropic principle spawned a possibly more controversial physical idea, that of the multiverse. If you want to start a bar fight amongst physicists, utter one word: multiverse. In the melee, shouts of being unscientific nonsense meet accusations of cosmic small-mindedness. Why should a single idea ignite so much bad blood across the community of physics? To understand this, we first need to understand what the multiverse is and what it is not. It is important to start by noting that the multiverse is not really a theory of physics. It is just a scientific idea, just a hypothesis, proposed to solve issues like cosmic fine-tuning. In fact, the multiverse is not even a single hypothesis, but a collection of ideas. But let's try and understand how the multiverse might be a solution to cosmic fine-tuning. The story starts with the greatest hope of late 20th century physics. We have already touched on the hunt for the theory of everything, the one theory to unite them all. And in the last decade of the 20th century, all hopes were focused on string theory. The notion that at the fundamental level, everything is composed of vibrating fundamental strings. What differentiates the various apparently fundamental particles is the way these strings vibrate, with different vibrations being different particles, one vibrational note for electrons and another for quarks. But the mathematics of string theory is insanely complex, and the theory has morphed and evolved. Today, many keen minds churn the numbers of string theory's descendant, what is known as M-theory. M-theory has yet to prove that it is the true path to salvation in the hunt for the theory of everything. But one dashed dream caused physicists to pause and reflect on their efforts. They had hoped that string theory would yield a single answer for the theory of everything. From their mathematics, the unique physics of our universe would emerge. Instead, the mathematics of string theory held an immense multitude of theories of everything. Over what's known as the string theory landscape, there is physics where gravity is stronger, or gravity is weaker, or where gravity is completely absent from the laws of physics. The same is true for the other forces, and even forces that we don't appear to have in our universe. All kinds of fundamental physics can be found jumbled up somewhere in the landscape. The number of possible combinations of fundamental physics is huge, possibly infinite. And as we have seen, from the fine-tuning argument, most of these are dead and sterile. The multiverse appears to be a lonely place, where habitability is extremely rare. So why, out of all the possibilities, does our universe have precisely the physics that allows us to be here? Enter the multiverse. The basic idea is that it all comes down to chance, a cosmic roll of the dice. Our universe is simply not alone, but there are many, many universes out there in the multiverse. When each of these universes was born, it was imprinted with its own fundamental laws of physics, with each combination of physics being drawn at random from the string theory landscape. How many universes must be out there for there to be a chance for our universe to be selected? A conservative estimate puts the number at more than 10 to the power of 500. Some suggest there are many, many more, maybe an infinite number. Our universe would be a rare, habitable cosmos in the legion of dead universes. This is a reflection of Dickey's anthropic idea, but now applied on an immense scale. And of course, we should not be surprised to find ourselves living inside a habitable universe. As if it were not that way, we would not be there to question the cosmos we see around us. But the cosmological cost is an almost infinite sea of dead universes out there somewhere. Many questions remain, such as how is the immensity of the universe created? Maybe they're constantly popping out of the quantum nothingness as quantum fluctuations. Or perhaps there is no ultimate origin, as we push things back into the infinite past. But some claim the multiverse is inevitable, from a strange feature seen in the early life of our universe. Many scientists think that our universe underwent an extreme bout of expansion when it was young. In the timeline of our universe, we mean about a trillionth of a trillionth of a trillionth of a second old. And this bout of expansion was over in a trillionth of a trillionth of a trillionth of a second. But when it had finished, the universe was about 10 to the power of 40 times larger. This cosmic inflation smooths out the universe, solving some puzzles in our astronomical observations. This means that most cosmologists are certain that inflation took place in this early life of the universe. It's thought that the driving force behind inflation was a strange energy field called the inflation. But quite what turned the inflation on, and why it turned off again, remains murky and mysterious. This has led some cosmologists to extend inflation into a much larger idea, that of eternal inflation. What if inflation began long ago, maybe an infinite time ago, and is still going on today? In this immensity of inflation, calmer bubble regions would freeze out of the roar of inflation. And the birth of our universe was just such a bubble region freezing out. As inflation grinds to a halt within a bubble, the energy of that inflation floods into the new universe. This would ultimately be the source of all the matter and radiation within the baby cosmos. But out of this flood of energy, the fundamental properties of the cosmos are crystallized. And each baby universe would be baptized with its own unique laws of physics. It's important to realize that the scale of these bubbles is immense, much larger than the observable universe of stars and galaxies we can spy through our telescopes. But far beyond our horizon, inflation continues to roar unabated. And new bubble universes condense out of the turmoil, each time with its own laws of physics. Eternal inflation is the engine for producing a multitude of universes in a multiverse. And our cosmic home is just one of the countless bubbles to have frozen out of inflation. Of course, in this lottery of physical laws, ours won the jackpot in terms of the laws of physics. And we find ourselves in one of the rare habitable universes in the extensive multiverse. To some, this picture seems entirely reasonable and neatly solves cosmic fine-tuning. but others claim they have pushed the envelope too hard and strayed into metaphysics. All these other universes out there in the endless eternal inflation are beyond our reach, and if we can never know if they exist, are they even a part of science? It is this that usually sparks the arguments and fights in bar rooms. One group sides with the ideas that the multiverse just seems so natural, a consequence of inflation. Others claim invoking the multiverse is little more than giving up on the search for true cosmic meaning. For if our universe is not unique, mathematically unique, how can we find ultimate answers? But remember how we started with this story, with the notion that the multiverse is just a hypothesis. It is a scientific idea that needs to be fleshed out before really understanding its physical meaning. Perhaps, with enough mathematical effort, someone will crack the code, and the multiverse will be science. And its imprint, with all of its other universes, will eventually come into our scientific grasp. Even if the multiverse idea is correct, there is still some disquiet among cosmologists, because it seems just so wasteful, so many dead universes for just a few that are habitable. Perhaps there's another way, a way that is not so deadly for generating universes. Perhaps we need to bring ideas from the evolution of our life into the life of universes. The name Alfred Russel Wallace should be better known among the scientific greats. Through the early 19th century, Wallace left his job as a civil engineer and decided to travel. He spent his time exploring the wilds of the Amazon basin and across the Malay archipelago. And as he did, a strange new idea about the abundance of life began to stir in his mind. As he explored the birds and the monkeys and many other animals, he realized that natural barriers such as mountains and waterways can separate populations. When separated, these populations appear to adapt to their local environments. And given enough time, these local populations could become their own species. Wallace began to publish his finding on the creatures he encountered and his ideas on life. And by the mid-1800s, his publications found their way to a naturalist in England. A little over a decade earlier, this naturalist had returned from his own voyage of discovery. And on his travels, this man, named Charles Darwin, had reached his own conclusions about life on Earth. Darwin is, of course, famous for his theory of natural selection, the survival of the fittest. Individual species, he claimed, evolved from isolated populations adapting to their local environment, with perhaps his most famous example being the specialized finches spread over the Galapagos Islands. However, Darwin had sat on his ideas, steadily building his arguments for the evolution of life. With the news of Wallace's findings, Darwin realized he was going to be scooped on his ideas of life. He was spurred into writing down his ideas of natural selection. In short order, he finalized his academic papers and wrote his now famous On the Origin of Species. And his position as the father of evolution and natural selection was set. Darwin did not ignore the contributions of Wallace, writing back and forth on their ideas. They presented their ideas jointly to the Linnean Society of London. And when Wallace returned from his travels in 1862, he became a defender of Darwin, promoting his precedents in developing the ideas of evolution and natural selection. In the early 1990s, physicist Lee Smolin wondered about cosmological natural selection. What if there was a process that acted to select life-bearing universes? Universes like ours. And just how would this process operate? And just what fitness is being selected for? Smolin realized that the secret was in one of the universe's most mysterious of objects: black holes. Black holes are completely collapsed objects, formed in the explosive deaths of massive stars. Smolin's idea is that when a black hole is formed, space and time are curved to an infinite extent. And in this extreme state, new space and new time can be formed, giving birth to a brand new universe. Within our observable universe, there are about 50 million supernovae per day. These are the explosions that occur when a massive star dies, collapses, and explodes. And so, if Smolin is correct, many millions of new universes are born every single day, each erupting from their mother, our universe. This baby universe is not an exact replica of its mother, with its physics ever so slightly varied. This mirrors the passage of genetic material from parents to children in life on Earth. And if this baby universe can too create stars and black holes, it can give birth to its own baby universes. So the process continues, generation of universes after generation of universes. Of course, any baby universe that does not inherit the ability to form stars and black holes is doomed. It would be an evolutionary dead end, like the dodo, unable to spawn any descendants. So those that remain similar to their parents will flourish and dominate the populations of universes, with glowing stars and black holes, and potentially life across the multiverse. But still, how did life sneak into this bout of cosmic natural selection? Remember that all of these universes need to produce stars, and stars produce chemical elements. The carbon and oxygen, iron and sulfur necessary for molecules and complexity. These are the vital ingredients for any form of life in any universe. And so, maybe all would be alive. Whilst Smolin's ideas are attractive, the usual question of the ultimate origin remains. Does this mean that a whole host of evolutionary dead-end universes existed before ours was formed? And if this was the case, what was the process that was responsible for forming new universes? It seems that the inclusion of cosmic natural selection just complicates the picture. We are rapidly approaching the close of our tale, but with more questions than answers. The creation of our universe remains as mysterious today as it did a century ago. Many ideas swirl in the mix. Ideas of multiverses and quantum nothingness. But what are likely to be the next steps? The hunt for the theory of everything continues unabated, as physicists prod and poke at M-theory, whilst new approaches are proposed. We don't know if or when we are likely to crack the mathematical challenge. But once we do, many secrets of the universe will be secret no more. In the meantime, let's look again at that dot. Soon, the mathematical door that has been closed for centuries will be pushed open. And cosmologists will rush to see what is beyond, what happened at the moment of cosmic creation. Perhaps they will find that some had guessed correctly, be it a nothing or a multiverse. Perhaps they will find that the universe was truly born 14 billion years ago, or maybe infinite. But perhaps, at the moment of creation, we will find something we never expected. And we will find that the birth of the universe was more beautiful than our wildest dreams. And in pondering on the enormity of this great expanse, exploring its present unknowns and fathomless beauty, we are wise to remember the beauty that surrounds us in our own lives. For here, on our pale blue dot, are mysteries and wonders of equal beauty to the endless sights of space. Imagine a single alien form sat on a distant outpost on some far-flung rock, gazing into our corner of the galaxy and spying this dot, watching the azure seas and great green woods and the flickering lights of civilization shining out as a beacon of community, yet unable to participate. Imagine they could peer at the peculiar beings upon its surface, so full of life, so mesmerizing. Us. Even from afar, our world's magnificence would be evident. We are unique. Our home is to be cherished. In the mundane, the day-to-day, the daily ebb and flow of life. So take a moment when you can to sit and gaze, not just up to the starry skies, but at the boughs and branches of the trees below, the shapes in the clouds, and the beauty of the sensations that surround us. Remembering there are no sounds in space, there are no trees, no clouds, no family dinners, no lovers' meetings, no books, nor songs, nor dogs, nor cats. We ought not to take those things for granted. It's within all of us, if we tune in, to have a deep connection to the beauty of our world. And then, for no reason other than curiosity, we can look to the stars for our dreams and ask what's out there, what else, that we might gaze upon in equal reverence to this home of ours. Jim Lovell. People often say, I hope to go to heaven when I die. In reality, if you think about it, you go to heaven when you're born.